Hello everyone, welcome back to Robotic Mechatronics System Design course, Lecture 6, Pneumatics, Air Preparation and Vacuum. So this lecture will conclude the whole topic on pneumatic part of the Robotic Mechatronics System Design course, and we could conclude our discussion on this topic. Today's topics are as follow: air preparation, compressors, pressure control valves, air services, piping system, and vacuum that includes Venturi effect, filter, and vacuum switch or negative pressure sensor. Air preparation. Compressors. So in this picture you could see one of many available compressors in the pneumatic systems. This is an exact compressor we have on the MPS 500. You see that we have a reservoir and the pistons and cylinder is here, and plus we have a regulator and the basically the air service part. The compressor symbol in a pneumatic system plus in Festofluid sim, as you could see, it's like this. You may have seen that we only have the triangular symbol, and that one is also another alternative for this symbol. So both of them represents compressor. The variable compressor, the one which has a variable capacity and the variable reservoir and the variable volume, output volume, air volume is represented by this symbol, and you could see this arrow here. So this arrow shows that we have this capability of changing the output volume. Air pressure. In pure pneumatic control chain, we have these basically tree, I could say, or hierarchy. The power part is the compressor, and that provides the high pressure air to the system. We have usually between 6 to 7 bar pressure for the main parts. So what are the main parts? Are directional valves and actuators. So we need a higher pressure to provide the proper force and power at the output, and we could have a lower pressure from 3 to 4 bar for sensors. I mean sensors, pneumatic sensors, not the electronic sensors, yes. So for pneumatic sensors and for logical circuits. So for the pilot lines, for example, and control valves. So mostly for the pilot lines and the signal lines, you could have a lower pressure, and that's why you usually see a smaller diameter for those ports. Okay, so here in this table we have units for force and pressure. The scientific unit for the force, the SI unit, is Newton, and for the pressure is Pascal, is Newton per square meter. Practical units for the force, for example, is kilogram force, and for the pressure is bar, which is kilogram force per square centimeter. and 1 kilogram force is equal to 9.8 newtons. So basically weight of 1 kilogram mass. So that weight of 1 kilogram mass is equal to 9.8 newton, and we could use that in as a unit. This is not the standard unit, but it's widely used and is a practical unit. 1 bar is almost equal to 100 kilopascal. So 1 bar is a pressure of atmosphere at the sea level. So at the sea level, we have a pressure of 1 bar at the atmosphere, which is exactly equal to this number, or almost is equal to 100 kilopascal, and is equal to 14.7 psi, which is pound per square inch in the American system. Compressor types, we have huge variety of compressors, and the two main branches are positive displacement compressors and the dynamic compressors. The positive displacement means that we are displacing air by a piston or an object, and dynamic because we are using a dynamic properties like a velocity and the acceleration of the air molecules and the air flows to basically change the pressure. For the positive displacement, we have two main branches, the rotary one and reciprocating. So reciprocating and rotary. So reciprocating ones are single acting, double acting, and diaphragm. So reciprocating ones are those like a cylinder and piston, the traditional one and the widely used one in the small systems. So single acting is the one, for example, we have on the MPS 500, and we already presented the picture on the previous slides. The rotary one, we have a lob, screw, liquid ring, scroll, and vane type. We don't have enough time to basically go and show you all these type of compressors, but however we selected a few of them. So those with a basically red ellipsoid border, so screw and the double acting and centrifugal will be presented in coming slides. The rest of them you could simply search it on a web, Google it, or find or basically refer to the reference books for further studying. The dynamic branch includes centrifugal and axial compressors. Okay, so as I said, we will explain the screw, the double acting, and centrifugal compressors in coming slides. So the double acting is one of a few types of reciprocating compressors. So you see that it goes through 4 stages, 1, 2, 3, and 4, to compress the air and to increase the pressure. At the first stage, so why we are calling this double acting? Because we have 2 cylinders and 2 pistons here, as you could see. We have a crank here, and goes through the first stage and the second stage. You see that the volume of the first one is larger than the volume of the second one. So at the first stage, the first cylinder will suck the air into the chamber. So we have air here now, okay, and now the air will be compressed. Okay, so the air will be compressed by moving the piston, decreasing the volume, and now we have a high pressure air. So look at these valves. Of course, these valves basically go through an orders of opening and closing. For example, in sucking stage, the first one is open and the second one is closed. For the basically compressing stage, both of them should be closed to the certain degree, and then the second one should become open to exhaust the air. So now we have a higher pressure air. You see that the temperature increases in this stage. That's why we have a cooler here, and that cooler here will decrease the pressure. It will help us to basically pump the air to the smaller volume, plus it helps us to stage the pressure and increase the pressure in the second stage. Now the second cylinder will come in effect and will compress the air, and finally will exhaust the air to the output. Okay, so we go through 4 stages from the first cylinder to the second cylinder, and also absorbing the temperature here and dropping the temperature between these 2 stages to achieve higher pressure. Screw compressor, as you could see in the picture, air compresses between 2 screws rotating on opposite directions. So we have 2 screws here that are rotating opposite of each other. One of them, let's say, clockwise, and the other one is rotating counterclockwise. And we are sucking air here through this port, and air goes between these 2 screws. The volume decreases as we go forward, and by decreasing volume we could increase the pressure. Again, these type of compressors are positive displacement compressors. Why? Because we are decreasing volume, very similar to the piston and cylinder, and by decreasing the volume we are increasing the pressure. The centrifugal compressor is basically, it belongs to the branch of dynamic compressors. It's useful for high air volume, and it converts kinetic energy into pressure energy. So we are using a kinetic energy, velocity, and acceleration of the air to change the pressure. So, so you see that low pressure coming from one side, and we could achieve higher pressure at the other side at the output. It's a very complicated compressor, and these propellers should be designed properly. I could say designing these propellers is a specific topic, is one full course. How to design these blades and how to basically design the chamber and the whole system. So I think it's beyond the purpose of this course. It's just for the sake of introduction to the compressors, and we don't have enough time to spend on this topic. Pressure control valves. We have pressure sequence valve and we have pressure regulating valve. Pressure sequence valve. If the pilot pressure reaches the preset pressure, then the valve will be activated. So that's why we call it pressure valve, pressure sequence valve. So there is a sequence between the signal coming in the pilot line. This is the pilot line here. This is a pilot line here, 12. Remember that the pilot lines should be numbered by 2 digits. So we have a pilot line, and when we send a signal and when the pressure in this signal line or the pilot line reaches to the preset value here, then the main valve will be activated. So what is the mechanism here? For example, here you could see that we have a spring. That spring cannot be pushed back until the pressure reaches to the setting value. And when it reaches to that specific value, then the spring will be pushed back and will have an opening. Will have an opening to the output. Okay, so this is the opening to the output. The port 2. So usually we have a set screw and we could change the preset value for the pressure. As you could see here, we have this arrow that shows we could have a variable preset value. And this is one type of pressure sequence valve. You could see one industrial application, a sample of these type of pressure sequence valves, and the symbol here that you could find in Festofluid Sim. Okay, example 1 on this topic. You want to have an indirect control of 2 double-acting cylinder. Positive control signal is manual, and the negative control signal if the input pressure of the cylinder reaches 4 bar. Okay, so we want to have a specific input pressure before activating the cylinder. The practical application and the reason for this specification is that, for example, we want to have a reliable, consistent power at the output. Without that consistent power, we don't want our cylinder to be moved or activated. The pressure of the compressor is 6 bar. Let's go through the solution. Again, I recommend you to build this circuit in Festofluid Sim, test it by yourself and see how it works. So you see that we have a double acting cylinder, a 5x2 main valve. We have 2 secondary valves. One of them activates the cylinder for a positive movement or the forward movement manually, and for the backward movement we have an automatic control and the sensor A1, which is located at the end of cylinder stroke. We have an adjustable speed here, and we have a pressure gauge. You could find it in Festofluid Sim, this pressure gauge. And when you start the simulation, it will show you the exact air pressure and the numbers and digits. Okay, so for the negative control or the backward motion, we want to reach specific air pressure. So we want to reach 4 bar here. That's why we have this pressure gauge here, just to examine the or circuit and see if it works properly. Okay, so this pressure could be used as a pilot or the signal pressure. Okay, so once it reaches to the 4 bar, where that 4 bar could be set here. So you will double click here and you will set the preset air pressure to 4 bar. Okay, so once it reaches to 4 bar, then this valve here will let the air passes from the port 1 to port 2, and the main valve will be activated. Okay, so do the test by yourself and see how basically the system works here, and how this pressure sequence valve could satisfy the specification of the example 1. Another valve is a pressure reducing or pressure regulating valve. The pressure regulator valve regulates the compressed air supply to the preset nominal pressure and equalizes pressure fluctuations. A valve that reduces or restricts pressure. So we want to equalize pressure fluctuations. So of course the output of a compressor, the output pressure of a compressor is not constant and consistent. However, in our system, we want to have a reliable, constant air pressure. So to avoid fluctuation of the pressure at the output of a compressor, it's a very common practice to have one of these pressure regulators or pressure reducing valve. So I will explain why we call it reducing. So let's see how it works here, and I will explain the symbol. Here we have a schematic diagram or the cross section of a pressure regulating valve with relief port. We have an input port, and this port is connected to the output of a compressor, and we have an output port P2, which is basically connected to the main line or zero line of our system. So the air comes from this port P1, will come to this chamber here, okay, and we have a spring here, and we have a set screw that we could change the compression of the spring here. And for example, when the pressure is high, that will push back that spring up, so it will increase the volume here in this chamber, and this will automatically drop the air pressure. And if the pressure is a bit lower as is desired, the spring will push back, will decrease the volume here, and it will increase the pressure. Of course, this spring is not designed to compress, or I could say changes the pressure significantly. So it's not a compressor. Okay, it's not designed to, let's say, increase the pressure from 1 bar to 3 bars. No, it's just designed to regulate and equalize the fluctuation. Let's say it could affect the air pressure minus plus 0.2 Pascal, or sorry, 0.2 bar. Okay, but what happens if this pressure increases a lot? Okay, for example, we want to have a 6 bar at the output, but for some reason the pressure at the input will go to 7 bar. Of course, this spring is not designed and cannot basically drop the air pressure 1 bar. 1 bar is too much. So how could we then decrease the pressure and regulate the output pressure? There is no way except exhausting some air. So you see that, for example, on this picture, the pressure was too high and it pushed back this obstacle here, or this diagram here, far to the limit, and now we have an opening. See, we have an opening to the atmosphere. Okay, so it reduces the air by reduces the pressure by exhausting air to the atmosphere. So that's why sometimes we call this type of regulators pressure reducing valve, because they are mostly designed to basically cap the pressure at the output. So now let's come to the symbol and explain the symbol. We have port 1, which is the main port, P1, equivalent to the P1 here. We have port 2, which is the output port, is equivalent to the P2 port. We have a spring, a variable spring, okay, this spring here. You see we have this dotted line here, which is originated from the valve and backs to the valve itself. So it means that the valve itself could regulate or could adjust itself. How? By the internal air pressure. By internal air pressure, we could adjust the configuration of the valve. So the valve is smart and has, I could say, type of pressure sensor. Okay, what else we have in this symbol? We have a port 3, which is the exhaust port and is equivalent to these vents here. Okay, so pressure regulating valve with manometer. Same symbol, just we have a manometer here. And as you could see, we have intel, we have an outlet, and we have a spring, and we have a manometer. And you see that how this spring could regulate the air pressure. We have a high pressure input, low pressure output. So you see that this dropping is reducing the air pressure because mainly they are designed to reduce the pressure at the input and cap it as to the desired one, and we have a system pressure loss. So if the pressure increases too much, then basically this piston will be pushed back completely and the air could be exhaust from this port here, and this is the port 3. Pressure reducing valves symbol. Here we have a pressure reducing valve symbol. I already explained that this one doesn't have exhaust port. The variable pressure reducing valve, just we could adjust the spring. Pressure reducing valve with relief port and pressure reducing valve with relief port, which is a variable. Okay, so we are done with the topic of compressors and pressure regulators and pressure sequence valve. Now we'll continue with parts and valves in preparation of compressed air. So let's say we already compressed the air, we regulated the air. What else should we do to have a proper air input to the system? We could have a drying unit. That drying unit basically will absorb the humidity of the air. We have different types of drying units. Absorption, which is a chemical basically reaction. Adsorption, which is a physical reaction. We have a low pressure drying or condensing. We could have air filtering, and air filtering is for basically filtering any dust or any particle in the air. And humidity absorber is another type, basically I could say not equivalent but alternative to the drying units, and these ones basically will absorb the humidity. I will explain what are the differences between these ones and the other ones. And you could have an airline lubricator. So airline lubricators will add some oil to the air, and droplets of the oil will move by the flow of the air and will reach to moving parts like pistons in cylinders, like spool in directional valves. So all of those are mechanical parts and need some oil. Otherwise, they could be degraded as they work, and we need lubrication to decrease the friction. Moisture, gases, or dissolved materials from the air combines with the desiccant to form into a solid or liquid state. It is a chemical process and no external energy is required. Simple installation but high operating costs because the desiccant have to be discarded. So we have a desiccant, it's a type of it's a chemical, it's a material. And then we have input air, let's say coming from a compressor, and moist air is a normal moist air, yes. So why we have humidity or moist in the air? Because the compressor is getting air from the atmosphere. Yeah, so it depends on the humidity of the city, of the environment, but anyway we have some level of humidity in the air. So now this air comes and will the water, the moisture will make some chemical reaction with the desiccant, and then at the output we have a dry air. Some part of the moisture could be condensed in this section, okay, and could be removed from the system or drained from the system. However, the majority of that will make a chemical reaction with the desiccant. So we need to change the desiccant, otherwise the absorption drying unit won't work, because the desiccant is already saturated and the whole basically material already made a chemical reaction. Another type of drying units are physical adsorption. Moisture, gases, or dissolved materials from the air deposits on the porous surface of the desiccant. It is a physical process and regeneration is possible through hot airflow. So here we have lower costs for changing the material because we could regenerate the material. We could basically dry the material. Let's see how it works here. This is a one industrial sample. Here we have an input air that goes through this filter or pre-filtering just to get the dust. Now it will divide it in two branches, the right one and left one. First, let's say the right one is closed or shut off, already closed. The other one is open. Okay, so the air will come to the first chamber or adsorber 1, and the adsorber 1 will be saturated after a while with the moisture, and you see that the dry air is the output of this chamber. Now after a while this adsorber will be saturated, so we need to regenerate that. So this valve will be closed and the other one will be open, and the air will go to the second chamber. So let's assume that this adsorber 2 is already saturated and this one is working, and now we want to regenerate the adsorber in this adsorber 2 chamber. We have a blower and we have a heater. Okay, so we have a hot air. This hot air will be blown into this chamber. So the hot air will pass through this material adsorber 2. The hot air will evaporate all the water inside this adsorber 2 chamber, and will be ejected from this pipe. Okay, so the heater will dry and will regenerate the adsorber 2 chamber, and this desiccant here will be ready for absorbing the humidity of the air. So we could basically cycle between the adsorber 1 and adsorber 2 chamber to basically to have a proper sequence and a high quality desiccant to dry air. Another type of drying units are refrigeration drying. Refrigeration drying, if the temperature is lower further, the water vapor contained in it begins to condense. Okay, and you have already observed that in your refrigerators, and you've seen that the humidity of the air will be condensed in your freezer or refrigerator. Let's go through the mechanism here and see how it works. So we have air intel from the output of the compressor. Okay, comes here. Okay, I will explain what is that exchanger, heat exchanger, later. Okay. Okay, so we have the air input here, and we have the refrigerating unit here. So the refrigerating unit or refrigeration machine will drop the temperature inside this chamber. Okay, so now we have a cold air here. We have a cold air. Okay, when we decreases temperature, it will condense the humidity of the air, and that humidity could be removed or drained from these moisture separators. Okay, so we just open the valve here, and we have water at the output. Okay, now we have a dry air here. However, this air is cold. Okay, we don't want to send this cold air to, or basically to the circuit or pneumatic circuit. So it will passes through this heat exchanger. At the heat exchanger, basically we are exchanging the heat between the air intel and the output dried inter. So the temperature here of the air will increase. It will absorb some energy from the input air, plus the temperature of the input air will drop. Okay, because ultimately we want to drop the temperature of the air here, and that will save some energy. Plus, when we drop the temperature of the air here at this stage, then some part of the humidity will be condensed, and we could drain that that water from this moisture separator. So this is the whole mechanism to dry air. Air filter, and so we need to filter any dust and obstacle. We don't want to send those obstacles to our moving parts and directional valves and cylinders. Those are expensive parts. Plus, they could destroy our system, and they could increase the friction. So we don't want dust accumulates inside or valves, inside or cylinders. Those are expensive parts, and basically without filtering them, we need to change those parts more often. Okay, so what is the good practice to have an air filter at the output of compressor? The compressed air filter removes contamination from the compressed air. The size of the filterable particles is dependent upon the filter class. Okay, so this is a symbol here that the air comes, passes through this filter here, and then we have the output port here.
This one is a manual air filter, and this one is automatic air filter. This one, we have a filter, plus we could drain the water at the bottom. Okay, so we have a condensate water here. Why we have a condensate? Because of the Venturi effect, and because of some changes in the pressure here and Venturi effect, some part of the humidity will be removed from the air, and we have a condensate here, and that part could be drained by this drain screw. Plus we have a filter. Okay, plus we have a filter. On the automatic part, that water will be removed automatically after when basically the water reaches to specific level. Okay, in the manual part, we need to drain those waters basically manually. So we need to open the valve here and drain the water. Airline lubricator, adding oil based on Venturi effect or vacuum. Air flows through the lubricator. Some of the air flowing through the valve is guided through a nozzle. Due to the resulting pressure drop, oil is drawn from an oil reservoir through a feed pipe. Okay, I will explain it in the picture. So here is the airline lubricator. We will feed this reservoir with oil. Okay, so we have oil here. We have input port, output port, and we had this feed pipe here. Okay, and we have our Venturi here. Okay, so here is a Venturi, to be exact, is here. And in the schematic part, you could see the Venturi. So what is Venturi? Okay, Venturi is basically is a narrow pipe. Okay, so so you see the diameter of the input port is constant until it reaches to the Venturi. Okay, so the diameter will decrease, and we have an orifice basically shape here at the middle, and the diameter at the output here. Okay, again it will be consistent and normal. Okay, so we have decrease in cross-sectional area here. We call this shape Venturi. Okay, so what happens when the diameter will decrease, then the velocity will increase, the velocity of the air will increase, and when the velocity will increase, the pressure will drop. Now we have a lower pressure here at the neck of the Venturi. I could say this is the neck of the Venturi, and then it will create some type of, I could say, some sort of suction. So we could suck the oil here from this feed pipe. Why we have a suction again? Because at the neck of the Venturi we have lower pressure of the air. Here, let's say we have higher pressure, and this higher pressure will basically push the oil through this feed pipe, and here we have an adjusting screw, and droplets of the oil will be thrown into the air flow. So now you see that we have the droplets of the air droplets of the oil inside the airflow. So these droplets of the oil will reach to our moving parts by the air, and we could lubricate our cylinders or directional valves, and it's essential to any pneumatic systems. Here you could see the symbol. Okay, so we have a closed bottom here, and there is another type with drain, so we could drain oil from the bottom. So you see that the symbol somehow represents the system, and the oil which is sucked from the reservoir will be thrown into the airflow. Air service unit. The filter with water separator cleans the compressed air of dirt, pipe scale, rust, and condensate. The pressure regulator adjusts the compressed air supply to the set operating pressure and compensates for pressure fluctuations. The pressure gauge shows the preset pressure. The on-off valve exhausts the entire control. So this is an air service unit. We have a filter. Okay. We have a water separator here. We have a pressure regulator, and we have a gauge, pressure gauge. The air service unit simplified version. The service unit is made up of a compressed air filter with water separator and a pressure control unit. This is just a symbol for the air service unit. However, internal components are shown here. So you could find these symbols in Fluid. This is one example of air service unit. And piping system. Condensation in the system should be prevented. So you see that we need to prevent condensation. We need to condensate it in our drying unit. We cannot let the water to be condensated inside our pipes or inside our directional valves or inside our cylinders, because we will have an accumulation of water. Yes, the condensate can be trapped in pipelines at lowest points. Pipelines should be installed with downward gradient measured in the direction of flow, gradient 1 to 2%. So let's say this is a pipeline and it's good to have a gradient or inclination of 1 to 2%. So anyway, even if you use a drying unit, the water will be concentrated. And we need to accumulate that somewhere in our system and drain it from our system. So it's good to have a gradient of 1 to 2%, and then we should have a draining valve to drain the water. Ring circuit are the commonly used pipeline installation. Gas can flow from two directions and a uniform supply can be obtained where there is heavy consumption. So we have a branch line. You see that the compressor, and these are, let's say, stations and units. Or we could have a ring circuit. We have a less pressure drop in the line, and the pressure is, I think, is more balanced in our system than this branch line, and this ones we have more pressure drop in the line. Interconnected piping system, higher cost but much less pressure drop in the network. So this is one example of interconnected systems, and we have less drop in the pressure of the system. The next part of this air preparation slide is vacuum. I think we had enough for this video and this lecture. We will continue in another video and in another lecture, and I will explain the vacuum part.